So here we go, and let's get started. So there's a question regarding, please also do tell what kind of business we can do with the knowledge computer vision. Well, most of the applications of computer vision fall under the product development, and the kind of applications we can do is, in terms of business, I would say you can start with a product-based company, and in that you can start providing services to businesses regarding that. A lot of businesses, government organizations these days are looking for computer vision applications, which could be based out of, let's say, CCTV cameras to security services, and from there to services related to healthcare applications and devices. So definitely I will have a good, you can say, a review of the business applications that we are, which are present in the market at the moment, and can be also used to monetize and create a business solution, right? So with that part, let's get started, everyone. So I would encourage, again, as I said, to ask as many questions as possible, but yes, make sure that we don't dive deeper a lot into basics of or fundamentals of neural networks. I'll try to give a very quick review of fundamentals of neural networks going further. Okay, so here we go, and let's start with understanding of images. All right, what is an image? Well, a picture or an image, as you can see, my one as well, right? So an image is composed of pixels, a lot of pixels, right? An image is collection of pixels arranged in a specific order. Mostly the images are arranged in the form of matrices. So you can think of an image as a matrix of pixels, right? It's composed of pixels. When I say what is, how is it arranged, or how pixels are arranged, you can say it's more of a matrix of pixels, right? So you have a lot of pixels arranged in a matrix format, and that's what composes an image. If I look at an example, it could be, let's say, this one. So if I take this part of image and try to stretch it a little bit more, zoom in side, you'll find that you'll have small boxes, right? So if you take one image and a part of it and try to zoom in a lot, you'll find that you'll have small boxes. The small boxes are nothing but pixels. Every box is a pixel. Every box is a pixel, right? And so you can say that there are boxes arranged in a horizontal and vertical way, which is like a matrix way. And these small boxes constitute an image, right? These small boxes hold a certain value. So how a pixel looks like, it's nothing but a mathematical number, right? A pixel is nothing but a numeric value. So first thing, images are composed of pixels arranged in horizontal and vertical order, right? And the other is what pixels look like. So generally, almost all the images in this world are processed in the size of 8-bit, right? So almost 95% of, I would say even 99% of computers, software, machines, cameras are programmed to process images in the binary size of 8 bits. So always images are processed in the binary format, like 0, 1 of size 8-bit. That means the size of every pixel, if I have to define a pixel can look like this: 0, 0, 0, 0, 0, 0, 0. This is one value of pixel. And you can say that this is lowest value of pixel, and the highest value of a pixel could be possibly, if it is a grayscale pixel, if you're talking about 1111, 1111, right? So yeah, this is how a pixel looks like. So you can say, in case of grayscale image, a pixel will be composed of a value. No, it's maybe it's part of the chat box, I believe that. Let me close that. Right. So sometimes in some of your machines, chat box might be closing or blocking a part of the screen. Right. I believe now it's on the left hand side, so that I need to keep open. I can keep it on left so that won't create any issue in the communication further. Right. So, but yeah, I would need that as a part of looking at your questions to be able to keep on seeing that out. Okay. All right. So going further, we'll we were discussing about every image is composed of pixels. Every pixel is composed, every pixel is like a small fundamental unit inside an image. An image is composed of so many pixels, right? And all the computers, software, machines, cameras, digital cameras mainly, are programmed to process images with value of pixels of 8-bit size. Almost all of them. Hardly there would be 1% of cameras and software which process images in other than 8-bit size, right? When I say 8-bit size, a value of pixel may look like this: 0000 and 1111, right? So this could be lowest value of pixel. Mostly this points out to black color pixel, and this 1111 points to white color pixel. If I try to represent this value in decimal format, you can say that a value of pixel can range from 0 to 255. Right, let me mute all the participants. There are all few participants who are on mute mode. Right, in case you have any question, you can put that in chat box. Yeah, so the idea is that the lowest value of pixel is 0 and the highest value it goes up to 255. In order to understand this much better, let's go ahead and do an example on this, right? So we're going to be going up and looking at an example to understand this much better. Okay, and in case you want to do that, you can actually also do that in Google Colab, right? So Colab is a free platform made available from Google for Python programming. So you can write a lot of Python code in the Colab, right? So I'm going to go to Google Colab and take a new programming notebook, and I'm going to be sharing all my notebooks to you post this webinar. That is end of tomorrow, right? Here we go, everyone, and let's look at the so this is going to be a bit of basics of images, I would say, the name of basics of images, right? So this is a Python code we're going to be looking at to understand a bit of basic fundamental of images. So let me import a few packages, which is could be NumPy as NP. If you have been already programming with MATLAB, you're going to find this super easy, and even MATLAB is super easy, right? So quite similar to that programming interface you're going to find here. So let's say I'm going to go ahead and create an array. X is numpy.array. I'm going to create an array with a set of values, which is going to be, let's say, 0, 255, 0, 255. As we know that pixels are composed of values between of 8-bit size, and in 8-bit size we can have values between 0 to 255, right? So I have 0, 255, 0, 255, 0, 255, let's say, and again another row of data 0, 255, 0, 255, and maybe let's say another row of data which is 0, 255, 0, 255. This is what we have as a part of data, right? Let's say this is an array, and we want to see this out as an image. I want to look at the idea of how this array would look like an image, right? So every image is actually an array or a matrix. You can think of that in that format, and let's try to visualize this array as an image. As we already know that images are composed of pixels. Every pixel is composed of a specific value or a set of values, and the values can range between 0 to 255 because all the pixels are of 8-bit size. 0 points to black color, and 255 points to white color. In case you think I'm going fast or something, please let me know about that. And this is it, right? Let's see this out. So this is a very fundamental image we are going to create here, which we have created here. As you can see, 0, 0, 0, 0, 255, 255, 255, like that column-wise values we have. As you can see that in the image, wherever there is a value 0 corresponding to, in the array, wherever there is a value 0 corresponding to that, we have more of a black color strip, right? So 0 column, black color strip, column of 255, white color strip, right? Again, column of 0, black color strip. So 0 color points to black color. The value pixel 0 points to black color, to value pixel 255 points to white color pixel. And for the current array, this is how it looks like, right? I hope we're good. Well, if I have a question for you that what should I make changes? What changes should I make in the current array if I have to create a chessboard of size 4 by 4? if I were to create a chessboard of size 4 by 4, what changes should I make in the current array? The current array is x 0255, 0255, 0255, 0255. Again, every row 0255, 0255. So if I have to create a chessboard image out of this, right? So I want to convert this into chessboard, right? So we want to see this image as a chessboard, right? Currently, what's happening? Wherever there is 0, it's black color, 255 white color. So what should we do if you want to convert this image or make it look like a chessboard? Right? In chessboard, you have white, black, white, black, white, black, like that. That's correct answer from Sutirtha, and we have correct answer from Tushar as well, and Shukwinder. Well, that may make a complete black color row, right? So alternate, that's correct answer from Abhishek and Ramachandra and Marco as well, right? So let me do that for you. What I can do is I can simply make it 2550, 2550. And similarly 2550, 2550, like this, right? And let's see this out. So, well, we should be able to get a chessboard image now, and as you can see, no, we can't see that. Well, let me run this again. Okay, so here we go, and we can see that now we got a chessboard, right? So wherever there's 0 value, corresponding the box is, the whole box is black, right? Wherever there's a value 255, corresponding the whole box is white color. 0 black color, 255 white color, 255 white color, 0 black color, 255 white color, 0 black color. Every box that you see can be thought of as a pixel. Every box here is a pixel. And what's the size of this image? So you can see the size of image is, what is the resolution of this image? The resolution of this image is 4 by 4, right? Like the way you see images have resolution like 1080 into 1920. Similarly, this image has 4 by 4, 4 rows and 4 columns. And this is a simple image of chessboard, right? Black color is represented by a pixel having value 0, right? And white color is represented by a pixel having value 255. Okay. Now, what if I want to have somewhat called gray color? So 0 points to black color, 255 points to white color. What should I do if I want to have gray color? So maybe somewhere I should try out a value between somewhere between 0 to 255. I hope all of you would agree on that. Right, so I can possibly try out a value, let's say, maybe I can try out a lot of other values between 0 to 55, 50, 100, 125, as you said, right? And let me also try out 150, 200, and 255. So now you can see that between 0 to 255, whenever I go between 0 to 255, every value points to a different shade of black and white. 125 is almost a gray color, or you can say it would have been 127 or 128, possibly a half of 0 to 255, right? So this 125 is almost a gray color. 100 is like a blackish one, and 50 is more blackish one. 150 is a bit more whitish, and 200 is even more whitish, and 255 is pure white, right? Like that, we have different shades of black and white. So whenever you see a grayscale image, in that every pixel is composed of a single value ranging between 0 to 255, right? So 0 is pointing always to black color, and 255 points to white color. The value pixel cannot be higher than 255. If you pass any value higher than 255, it will truncate it to 255 and only give you white color. And yeah, that's about it, everyone. That's about it. So I hope now we have fundamental understanding of pixels and image, right? So I can write more pixels and create a shape out of this as well. It's just I have to change the arrangement of pixels, right? So let's say if I want to create a pixel or image of T from tech trunk, right? So I can kind of put here, let's say 255, 2550, 255 and 225, let's say, right? And I can do like this, maybe 0, 0, and a bit of changes can help in creating more of a T shape out of this. Like this is not very much I would say attractive, right? So let me do one thing, comma 0 and comma 0, comma 0, and so I forgot to pass a value here as well, which is, let's say, 255. So this creates a kind of T shape over here, right? As there is a 225, you can see that box is a bit gray, right? So if I were to create any image, every image is just arrangement of pixel. In this world, every picture, every photograph, every image is just arrangement of pixel in a specific order. When pixels are arranged in a specific order, that ends up to create leads to create a sort of image or a photograph, right? So that's an idea about it. And this was more on understanding about grayscale images. What if we talk about color images, right? How do we build color images? How do we put color images, right? So let's understand that as well. For color images, one of the fundamental idea is for color images, every pixel will have 3 values, right? For color images, every pixel will have 3 values, which will be red, green, and blue, RGB. These are standard space to represent color images. So in case of grayscale image, every pixel is going to have 1 value. For color image, every pixel is going to have 3 value. For example, if the value pixel is, let's say, 0, 0, 0, you can think of this as a black color pixel, right? So this all points to R, G, B. If the value pixel is, let's say, if the value pixel is 255, which is R, 0, and 0, that means this will point to red color pixel, right? As corresponding to red position, it is 255. For green and blue position, it is 0, 0. And if it is 0, 255, 0, which color it would be according to you? And you need to answer me for this one. And for 0, 0, 255, which color it would be? Right. So for the first one, 02550, it is RGB. As the position of green is 255, so it's going to be green. And for this one, if the value of pixel is like this, it would be blue. Similarly, it is all 255, 255, 255. It's going to be a white color pixel, right? That's how that's how the right. That's how the I will make it a bit smaller. I just wanted to make them in a list format, right? So let it be. Okay, so this is what we have about it. Let's create an RGB image. So you can say y equals np.array, and now we have to pass an image which is going to be consisting of rows and columns, but every pixel will have 3 values instead of 1 value, right? So we'll say that, okay, the first row and the second row. In the first row, we're going to have first column and the second column. Similarly, first column and the second column. So you can say here, so you can say that it's 2 by 2, right? 2 rows and 2 columns we have. For the first pixel, we'll pass a value, let's say 255, 0, 0. For the second one, we'll pass 0, 255, 0. And for third one, we can pass 0, 255. And let's say I've passed 255, 255, 0. Now this is a color image. I can do purely.im show y. So it says that I'm missing something. Oh, I'm missing a comma here. So now you can see that we got an image of shape 2 by 2, right? So it's of 2 by 2, 2 rows and 2 columns, but every pixel has 3 values. So if you look at y.shape here, you'll find that the shape is 2 rows and 2 columns by 3, 2 by 2 by 3. Every image, whenever it is a color image, the shape of image will be row, column, 3. 3 shows the 3 values RGB, or we also call it 3 channels RGB, right? As you can see that wherever we have put 25500, it's a red color pixel, 02550, it's a green color pixel, 00255, that's a blue color pixel, and 255, which is mixture of red and green, is creating a yellow color pixel. That means every other color in this world can be created by a proper mixture of red and green and blue, right? Again, you can do a lot of changes of shades of red, green, and blue, and that's how you can create any other color in this world. So all the color images are composed of pixels, but in case of color image, one pixel contains 3 values, right? So in y.shape, 3 represents that one pixel contains 3 values, which are R, G, and B. So there's 2 rows and 2 columns. That means there are total 4 pixels, right? 2 rows and 2 columns means what? There are total 4 pixels. Each pixel contains 3 values, right? So whereas similarly, if you look at X, which was a grayscale image, here it shows the 4 by 5. So there are 4 rows and 5 columns. That means total 20 pixels. Now, comma 1 is not there, but that means each pixel contains 1 value. Here, each pixel contains 3 values, right? That's the idea. I hope you're good with this. Okay. So I hope now, by now, we are all good with understanding of fundamental idea of what are images. Now let's move further. Next is computer vision. So shifting back to further to computer vision. Computer vision is a very vast field. There are a variety of tasks that we do in computer vision, which include the tasks like the very fundamental task, which we're going to be starting out with, is the understanding of classification. In classification, we try to tell that, well, this image is input, and the output is cat. You can say that it says that, okay, this image is having cat. So in classification, we just pass the image, and the algorithm or machine learning or deep learning algorithm is going to tell us what is the object in that image. What is the object, not where is the object, right? Then we have something called classification plus localization, in which we pass one image with one object. The algorithm is going to tell us that, well, this image is having cat, and this is the bounding box, right? This is the bounding box where cat is present, right? This is it's actually a chat box, and it should not actually, it should say transparent, and I'm gonna just move it somewhere down. Okay, so yeah, here we go. So classification is a very fundamental task where we talk about sort of passing an image, and the output is that it says the machine learning or deep learning algorithm or the neural network is going to say that this image is composed of cat. Whereas localization, in which we pass an image, it's going to say that, okay, this image is composed of cat, and these are bounding boxes. So it's going to predict x1, and this is x1, this is y1, and this is x2, and this is y2. So the algorithm is also going to predict the name of object, as well as it's going to predict 4 values, x1, y1, x2, y2, which is going to create the bounding box of this image. Then we have something called object detection. For object detection, you pass an image, and there could be multiple objects. The algorithm is going to give the name of all the objects with corresponding bounding box. So it's going to say that there's cat1 with bounding box x1, y1, x2, y2. It's going to say that there's cat, there's a dog1, which is having x1, y1, certain value of x1, y1, x2, y2. There's dog2, which is having certain value of x1, y1, x2, y2, like that. Then comes up segmentation. Segmentation actually doesn't give you the bounding box, rather gives you exact area in which the image is present. So it's going to give you that, okay, this is the portion where the dog is there, and this is the portion where the cat is there, and this is the portion where the dog is there, right? The detection, you try to get the bounding box or the rectangle in which you may have some portion of the image which may not actually be dog. You can say this portion of the image. Whereas in segmentation, you get the most precise outcome is in, in which portion the dog or cat or maybe whatever the object is present. Right, so this is a bit of paradigm, or I would say landscape of computer vision. What are the typical popular tasks that we do under computer vision? Right, out of these all tasks, the one that we're going to be looking at is the first one, classification. In the upcoming session, we're going to be also having webinar in coming week, which is going to be I believe on localization and detection as well. So that's going to be quite interesting as well. So this week, or this particular webinar, currently we're going ahead with what we are interested into is classification. Right, I hope you got an understanding of the landscape of computer vision. Right, here we go. So in classification, what we do is we pass lots of images to the algorithm, and it learns very well how to identify different types of object. So we're going to be passing up a lot of images, and it's going to be learning how a particular object A and another object B looks like. And for any new object, the algorithm will be able to make prediction that, okay, this image is having A or the other image is having B. For any new image, it can say that this image has having cat and the other image has having dog. Right, so that's the idea. There's a question, please tell the classification and segmentation difference. Right, so Sarah, you see, in the classification, what you do is you just get the name of image, and it doesn't give you any information about on which position actually the image is, right? So in this image, if you pass this image, it may be possible this image is having cat. So classification only gives you that idea that this is cat, but doesn't tell you that this portion of the image is not representing cat. This portion of the image is not representing cat. This portion of the image is not representing cat. This portion of the image is not representing cat. Classification doesn't tell you this thing. Whereas segmentation actually outputs you the exact boundary. You see this exact boundary you get in the segmentation. And it says you, this is the boundary of a dog, and this is the boundary of a cat, and this is the boundary of the dog. So it actually segments, that means separates the background from the actual image and actual object, and also helps you to understand different objects, what do they represent, right? So you can see that it says that this is the boundary which is representing the dog. So it actually helps you to separate the object exactly from the background, right? I hope that helps you to understand the difference between classification and segmentation. Right. Segmentation is very widely used in the application of self-driving car to help the self-driving cars being able to understand what is a vehicle and what is a background, which vehicle is paused or not moving, which vehicle is moving, which is human and which is not human, the background and the tree, different objects. So tree, background, checkpost, road, barrier, corridors, different other things, and image, exact position of them, self-driving car engine can identify quite easily using with the help of segmentation. So what segmentation does is, as we said, it simply separates the whole object, and you can say that it might say like this, that this particular portion is representing a cat, and it will tell you that the other portion is representing the dog, like that. In localization, difference between localization and object detection. In localization, you talk about only one image, only one object. And here talk about multiple objects. Right, that's the main difference. So in localization, it's going to just work on the image level, but in object detection, it's going to work on the inside the image on the object level. Right. So yeah, that's the idea. I hope that answers the question as well. Okay. So considering that we're all good so far, we'll move forward, everyone. And we were talking about the idea of image classification. So what we're going to be working out with is we're going to be working with the idea of classification to understand that how classification actually works out. And we're going to be doing this with the help of neural networks. So far, standard neural networks, or you can say more of the weighted sum activation function-based dense neural networks have been very widely used for multiple tasks in computer vision and NLP and data science, right? But what we are more interested into is that what is the more appropriate approach for classification, which is convolutional neural network, and we are more interested in understanding that. All right. I hope you agree with that. Okay. So considering we're good so far, we'll move forward at the moment, and we want to understand a bit of fundamental understanding of neural networks, right? So let's go ahead and have a quick overview of fundamentals of neural networks in a quick go. So this is going to be, I'm taking it a little quick, considering that you already know this, because neural network fundamental is not expected to be part of this particular webinar. And as we are also lacking with time, it may become a bit difficult for us to cover up all of them. But though, in just for you to be able to have a quick repeat of that, we're going to be sort of taking an example. So, well, we can talk about something called neural networks. So neural networks are composed of, neural networks are nothing but computational units. And they're inspired from the way human brain looks like. So if you look at a human brain neuron, so in human brain, we have lots and lots of neurons over here, right? And this is a fundamental example of how a neuron looks like, right? If you look at here, you can see that this is a neuron, and it has a lot of dendrites. So you don't need to learn biology for sure, at least to be able to learn neural networks. This is just for intuition, right? And here we have a lot of dendrites, which in a neuron bring input to the neuron, and this is the cell body of the neuron. So dendrites bring a lot of input data from eyes, from ears, from nose, and that data is captured inside the cell body, and cell body takes a decision, and it generates some output which is forwarded to another neuron via axon. So in a human brain, we have a neuron which takes some input, does some computation, and generates some output, right? In a human brain, we have a neuron, natural neuron, which takes some input, does some computation, and generates some output out of it, right? So the way we have a natural neuron in human brain and the way it is arranged is like we have a lot of neurons connected to our input organs, eyes, ears, nose, right? So eyes and ears and nose and lips and skin and tongue. A lot of these input organs are connected to thousands and thousands of neurons. And then those neurons are further connected to millions of other neurons in our human brain. So every neuron does computation, passes output to another computation, another neuron is going to again do computation, right? So there are sequence of neurons connected. That means on the same data, there's a sequence of computation is going to happen. So let's say that if there is a neuron connected to our ear, so you can say this is neuron N1, N2, this is N3, this is N4. This is how a neural network could look like. This is N5, and this is N6, N7, like that. Now what may happen, let's say that if a human is listening, and let's say somebody, this is my ear, right? This is my ear, and somebody's calling me, hey Anshu, from the backside. So my data is going to go through neuron N1 to neuron, let's say N2. Neuron N2 is going to just check, is it a male voice or female voice, right? So it's going to check a male voice or a female voice. It's going to send data to N3. Let's say if it was a male voice, it's going to check it's an old age or it's a young age, right? So every neuron does some level of classification to understand that who is that, right? So as there are millions of neurons, they do very fast classification and calculation, and we immediately, our brain comes to know that, okay, that's my friend X or my friend Y who is calling me, hey Anshu, right? So whenever somebody calls us, we hear that voice, the ears bring, the neurons connected to our ears bring that data to brain. Multiple neurons do the job of computation on that data in a very quick go. As there are millions of neurons computing on that data, the human brain works quite faster and does very, takes very intelligent decisions and identifies the voice, identifies the speech, the scenery, text, a lot of these. So human brain is composed of millions of neurons, and that those neurons perform multi-level and multi-layer and multi-level classification or computation on data. Right. This could be an example of how human neurons kind of communicate to each other in a human brain. So they sort of send signal from, or you can say data from one to another, right? And that's how they keep on communicating. One neuron computes data, and it passes to another neuron. So the way we have natural neuron in human brain, in artificial neural network, we have an artificial neuron. So the way this natural neuron can actually take some data, perform some computation, and take some data, perform some computation, and simply generate some output. Similar way, a natural neuron can take some input, artificial neuron can take some input, do some mathematics here, and generate some output. So the way we have natural neuron which can take some input, do some computation, and generate output, we have an artificial neuron as well, which is nothing but a mathematical equation. You can think of this neuron as, let's say, y hat equals m1 x1, a linear regression equation, m2 x2 plus m3 x3 plus c. This equation, I can represent that using a neuron. So you can say that this equation is m1, m2, m3, x1, x2, and x3 plus the addition of c, and the output is y hat. So a single neuron is nothing but a single one linear equation, right? Every neuron, every linear equation can be represented as a single neuron, or every neuron can be represented as or thought of as a single linear equation. So M1, M2 are weights and X1, X2 are data. For example, let's say if I'm doing image classification, X1, X2, X3 may represent the value of pixels, and M1, M2, M3 represents the weight, or you can also think of them as W1, W2, W3, as in how neural network is going to learn that the combination of these pixels is going to help us to recognize whether it is A or B or C, right, like that, or particular object, cat or dog, right? So these are weights, or you can say the learning that neural network makes in the form of mathematical numbers. X1, X2, X3 represents the values of features, which could be pixels, which could be words in case of NLP, and features in case of data science, others like that. So that's an idea about it, right? That's an idea, I hope good. The way in natural neuron, the way in a human brain, two neurons communicate to each other. So one neuron is going to take some input, do some computation, generate output. This output will be taken as input by another neuron, take some input, do some computation, generate some output. Similar to that in artificial neural network as well, one neuron is going to take some input, do some computation, generate output. Another neuron is going to take that input from other network as well and do some computation, generate output. This is how two neurons are connected to each other. And this is how a neural network looks like. This is a typical example of a neural network, right? So you can say single neuron is a single mathematical equation, and like that, there are multiple linear equations connected to each other. So this is a neural network, or you can think of it as a typical artificial brain as well, right? In a neural network, you have neurons connected in layers, arranged in layers, I would say. So you can say that this is layer L1 of neurons, this is layer L2 of neurons, L3 of neurons, and layer L4 of neurons. There can be even more layers as well, and there can be even less layers as well. There are always three types of layers in a neural network. The leftmost layer is always the input layer, and the rightmost layer is always the output layer. And all the layers between input and output are termed as hidden layer of the neural network, right? So we have three types of layers: input layer, hidden layer, and output layer of the neural network. The number of neurons in input layer are equal to number of features. For example, if I have an image which is of 10 by 10, so how many neurons I will have in input layer? You can say 100 neurons I will have in input layer. If I have an image of size 10 by 10, I will have 100 neurons in the input layer. And let's say that with that image, I want to do 5 class classification, so I will have 5 neurons in output layer. So number of neurons in input layer are equal to number of features, whereas number of neurons in output layer are equal to the number of labels, you can say, right? And yeah, the number of labels. So let's say that if I'm doing face recognition and I have to do face recognition for 20 employees of my company, I will have 20 neurons in output layer of the neural network. And if each image is of shape 20 by 20, I will have 400 neurons in the input layer. So input layer neurons represent the number of features, which is like pixels in case of images, and the output layer neurons represent the number of labels or the classes, as in how many class classification I have to do. So yeah, that's an idea, everyone. That's an idea so far about the understanding of neural network, right? And what internally every neuron does is, in a neural network, every neuron does two-step mathematics. right? So you might want to understand that what happens here in the neural network, what happens here, right? What happens here in this neural network, right? What happens here in this neural network, or what happens here in this neuron of the neural network. So every neuron actually does two-step processing. First rule of neural network is no computation on input layer of neurons. That means in any neural network, input layer never performs any mathematics or computation on data. So you can see that in this neural network, we have total 4 layers, but only 3 computational layers, right? The input layer neurons are not computational, as on input layer neurons, there is no mathematics that is performed. Only from hidden and output layer, the mathematics is performed. The other is on every computational neuron, there's a two-step process that occurs, weighted sum activation function. The example of weighted sum could be, if I have input neurons as x1, x2, and x3, the corresponding weight are w1, w2, and w3. So weighted sum example could be, you can say here I will have z equals x1 w1 plus x2 w2 plus x3 w3 plus bias b. That's called weighted sum. And then on every weighted sum in every neuron, we have two-step process as we discussed, the weighted sum. So you can say that this is a neuron. This is a neuron. So here first step is weighted sum, second step is sum activation function. That means some function is going to be applied on this to get the output. Some function applied on Z, which could be sigmoid function, which could be identity function, softmax function, any other mathematical function, which mainly depends on what kind of problem are you trying to solve. Right, so that's a quick review of neural networks. I hope now at the moment there's a lot more to talk about neural networks, backpropagation, forward pass, and a lot of it. Right, so I hope now we are good so far with the fundamental understanding of neural networks, everyone. And this is the neural network in which every neuron does weighted sum activation function, and that's how it tries to do the job of classification. There's a question, what is the importance of B? B is extra bias or extra add-on, to the weighted sum calculation, or I would say the feature vector value calculation. What B actually represents, so it is also a type of weight, but which is not impacted by any input feature. Now let's say that in terms of calculation of output, there would be always some contribution to the features, but then there would always be an extra addition happening up to that, which is not contributed by the features, which is a constant presence of the features, right? And that would be attained by weight. For example, let's say if I give you a standard fundamental example of, let's say, housing prices prediction. If I have to build a model for predicting fare of let's say fare of Ola ride. If I have to build a model to predict fare of Ola ride, now the fare of Ola ride or Uber ride heavily depends on the number of kilometers, the source to destination, a lot of other features. But then there's a minimum fare available, which is 10 rupees or maybe 20 rupees or 50 rupees. That extra minimum fare is not impacted by any feature, number of kilometers, the source, destination, the type of cab, nothing. It is extra add-on to the whole fare, which is acquired by the value bias, right? So in every calculation, you may have some extra addition happening to the calculation, right? It may or may not be there. If that is present, when you train the neural network, that extra addition value will be acquired by the bias, and rest of contribution to the features will be acquired by W1, W2, W3, right? So here W1, W2, W3 show how much the feature X1 is important for the next particular neuron, right? So if I have to give you a bit more intuitive idea of this. Right, so let's say if we talk about a bit of neural networks. My bad. Okay, so let's say if a typical neural network looks like this, in which we have a typical neural networks looking like this. And we have something like, let's say that this neuron is neuron N1, N2, N3, and this is neuron N4, right? And we have N1. So in a neural network, all the neurons of layer 1 are going to be connected to all the neurons of next layer. So you can say this is layer L1, this is layer L2, and this is input layer, this is output layer. In the current neural network, we do not have hidden layer, right? And we have output as y hat, let's say. Now, whenever one neuron is connected to another neuron, how much important N1 is for N4, that is represented by a value called weight W1, W2, W3. So the weights W1, W2, W3 shows the importance of neuron N1, N2, N3 for the neuron N4. When you start to train the neural network, the values of neural network, the values of weights are randomly initialized. So there's a question about, do we randomly initialize that? Yes, we always initialize the values of weights randomly. But then there is another approach, Abhishek, which is what you call transfer learning. That's we're going to see tomorrow, which is the much better and the most appropriate way of initializing the values of weights, right? So yes, we start with random initialization in most of the cases. If I talk about a generic example, and W1 simply represents the importance of N1 for N4, W2 represents the importance of N2 for N4, W3 represents the importance of N3 for N4, and that's more of an idea about it. And then there will be constant addition to this, which is like bias, you can say, right? That's what you call. Now, as you know that input layer neurons, which is like L1 layer, are not computational layer, so there's no mathematics going to happen here. On every computational layer, there's two-step mathematics, weighted sum and activation function. So the first step is weighted sum. So you can say that first step is going to be Z equal X1 W1, where X1 is the feature. If X1 is the feature here, X2 is the feature here, X3 is the feature here, plus X2 W2 plus X3 W3 plus bias B. Whereas second step is output of neuron N4 can be thought of as some activation function of F applied on the weighted sum, right? The weighted sum. That's how neural network works out, right? That's an idea about it, everyone. Let me know if you're good. Any question that you have, right? So let me take a few questions. What you can repeat, what does the 3 represents in y.chip? Yeah, I have answered that. And how to initialize weights randomly, role of weight. So do weights actually help the neural network to learn the pattern, right? So whenever you say that neural networks are actually learning pattern, for example, if you think of a very simple example, when we were kids, we went to school to learn ABCD. We were shown a book, in which there was an image of A, image of B, C, D, E, F. The image of A was a picture, and the teacher's voice that this is A, this is B, this is C. And our brain was learning that, okay, this is how the pattern of A looks like, this is how the pattern of B looks like. At the end of the day, the book didn't go inside the brain. The book is as it is. The physical presence of book is as it is. So the book was not vanished. The data is not vanished. It just our brain started to contain few patterns of how A, B, C, D looks like. Similarly, a neural network, when you teach neural network with, let's say, 100 images of A and 100 images of B, or let's say 100 images of cat and 100 images of dog, to learn how cat or dog look similar or different than each other. The neural network is not going to memorize the images. It's not going to remember the pictures. It's not going to store the pictures. It is going to learn the patterns. And those patterns of how cat and dog look like, it learns and stores that in the form of weights. So the weights here help the neural network to understand that how different features are important to understand or important to identify whether it is a cat or it is a dog, right? So the weights actually are the real learning that a neural network actually makes, while when we train the neural network with a specific set of data, right? And the weights carry the learning of neural network, you can say. And here W1, W2, W3 simply shows how much N1 is important for N4, N2 for N4, N3 for N4, so on and so forth. If that answers the question, Joey, let me know if you have any question. Thanks, Amani, Raj, and I hope we are good, Abhishek, with the question of yours. There's a question: what range of values of weights and bias can be chosen for a particular application? Generally, you'd want all of your weights and bias to be normally distributed, with a mean of 0 and standard deviation of 1. Right, and there's no range in general. You can start with anything. There's no limitation to where to start. But in general, most of the times you want to have scaled value around 0, distributed normally around 0 with 0 mean. That means they are all normally distributed around 0 mostly. I'm using Microsoft One notebook. Amani, I'm using Microsoft's One notebook. It comes up with Office. Can you explain N4 equals FZ again, please, in short? Yeah, N4 is activation function. Activation function is some function which does a bit of transformation on the images, sorry, on the transformation on the weighted sum. This could be sigmoid function, this could be identity function, this could be softmax function, or a hyperbolic tangent function. Any other function it could be fx equal to x square, right? Technically, we generally do not use this, but it could also be fx equal to x square as well, right? So any function applied on this. This is a property of neuron. In every neuron, we have weighted sum and activation function, right? So there is a specific role of activation function. On the output layer, it decides whether the problem that you want to solve is a regression problem, or you want to solve classification problem, or you want to solve two-class classification problem or multi-class classification problem. So the role of activation function on the output layer of neural network is to decide what kind of problem this neural network can be used to solve. So if it is regression, you'll use identity as so the fx will be identity function, or it could be ReLU function if you're solving a regression problem with neural network. Fx could be sigmoid or tanh function if you're solving a two-class classification with the help of neural network. And fx, which is activation function, would be softmax if you're solving a multi-class classification. So the value of or the type of activation function that you would want to use always depend on what kind of problem are you trying to solve, right? So based on the type of activation function, based on the type of problem, you will choose the activation function on the output layer, not on the hidden layer. On the hidden layers, it's up to us which activation function do we want to use. But on the output layer, always the choice of activation function depends on what problem are you trying to solve with the help of neural network. Okay. So yeah, that's an idea about it. I hope that helps you with it. So we are good. There is a question, what is the base of selection of different activation function? Well, all of these activation do what? Activation actually module, you can say it mutates your output in a format so that you can use it for a specific problem. For example, regression. In regression, you always try to predict a numeric attribute. You try to predict age of customer, or maybe if I have to do age prediction from face, it is a regression problem. Now in age, you want to predict a numerical value, 20, 40, 50, 60, 80. And weighted sum could be that, right? So I can take for regression, I can take a sample activation function, which is fx equals x. That is identity function. That means there is almost no activation function, right? Because you would want to predict a numeric attribute, and it does the job. Weighted sum can easily be that numeric attribute, which could be possibly age, salary, or any other thing, height or weight, any other thing from the image or from any other source of data. But let's see, if I'm trying to solve a classification problem, and mainly in that too, let's say two-class classification. Now, in two-class classification, what is the format of output that you want? You want the output format to be either 0 or 1. That means the neural network should be able to say this is either cat or dog, right? I hope you agree on that. So in two-class classification, you would always want to have output either 0 or 1. But your weighted sum will not be 0, 1, right? Weighted sum x1 w1, x2 w2, x2 w3 plus b could be 20, it could be 30, it could be 40, it could be 50, it could be 100, it could be 500 as well. So what we do as a part of two-class classification is we use sigmoid function as an activation function, fx equals 1 by 1 plus e power minus x. Now this is a very much magical function. What it does is any value of x you pass to this function, the output will always be, so if I pass any value of x, the output will always be a value between 0 to 1, right? It will always be a value between 0 to 1. So I can think of this value as a probability, and I can threshold it. If the probability is less than 0.5, it is class 0. If the probability is greater than or equal to 0.5, it is class 1. So this is how we can sigmoid function is used to convert the weighted sum, which could be 20, 45, minus 20, minus 50, minus 100, plus 500, 1000. It is used to convert that in the form of 0, 1. Yes or no, like that. So sigmoid activation function transforms the weighted sum value into a probabilistic value. And that probabilistic value could be thought of as a probability of image to become a dog or to become a cat or a male or a female, right? And then we threshold with 0.5, or it can change as well, and try to identify whether it is male or female, cat or dog, like that. I hope that answers your question, Mr. Sekharappa. Sorry, Mr. Sekharappa. I hope that answers your question. Right. And this is the rule for output layer, right? So this is the rule for output neuron of neural network. Right. Next is there's a question: is hidden layer mandatory? It's up to us. It's our choice whether you want to go for hidden layer or not. Right. So let me show you an example to understand that better. So are we good so far, everyone? Any other question other than hidden layer? Let me know so that I can maybe possibly include that over here. Okay. So let me take an example to help you understand a bit of idea about hidden layers. Right, here we go. Output layer is the last layer of the neural network. That's correct, Justin. So here we go with an example. Let's see that out here, right? So let's say we have a neural network, right? So we have a neural network, and which is of 3 input and 1 output. So there are only 2 layers: L1 layer, which is input layer, and the L2 layer, which is the output layer. And over here, you can see that all the neurons of L1 are connected to all the neurons of L2. And this is neuron N1, N2, N3, and N4. Whenever there are 2 neurons connected, they're connected by something called weight. So W1, W2, W2, W3. And there's a bias connected over here, which is B. And then there is output. As you know that every neuron does 2-step processing, right? In every neuron, there is a 2-step processing which occurs. You can see here also there is a 2-step processing. If I have to say that like this, if this is N4 neuron, I'm going to write it here. The first step is weighted sum, and the second step is activation function. Okay. So this is N4 neuron, right? So the first step is weighted sum, second is activation function. So I can say weighted sum is, if these features are x1, x2, let's say n1 represents x1, n2 represents x2, n3 represents x3. So weighted sum could be x1 w1 plus x2 w2 plus x3 w3 plus b. And output of n4, which is, I can say, my y hat prediction as well, could be f of z, which could also be thought as y hat equals f of x1 w1 plus x2 w2 plus x3 w3 plus b. Okay. Now this is the neural network where we do not have hidden layer, right? Where we do not have any hidden layer. We just have input layer. We just have output layer. Okay. Now one of the important thing, if in this neural network, if I take fx as x, the activation function, which is identity function, then this neural network will look like an equation of linear regression model, y hat equal to m1 x1 m2 x2 m3 x3 plus c, and it can be used to solve a regression problem. If I take activation function as 1 by 1 plus e power minus x, which is sigmoid, then this would look like a logistic regression model, and it can be used to solve classification problem. Right? That means the job of activation function on the output layer is to decide whether the neural network will be used for solving regression problem or it will be used for solving classification problem. That's point 1. Now, can we say in both the cases, whether you take a regression model or whether you, whatever the type of activation function you take, can we say in both the cases, this equation is a linear equation? This equation is a linear equation. I hope all of you agree that this is a linear equation. And in a 2D plot of 2 features, I can think of this equation as a straight line possibly, right? So this equation is a linear model. It's a linear equation. So whenever you have a neural network without hidden layer, it cannot solve non-linear problems. It cannot solve complex problems, right? This neural network can only solve easy problems or linear problems. For example, if I show you two scenarios, let's say if I show you two scenarios, we have X and we have Y. We have another scenario of X and we have Y. And let's say the data distribution in first scenario is like this. And in second scenario, the data distribution is like this. Now, can we say in first scenario, when X increases, Y also increases? Do you agree with that? For a lower value of X, you have a lower value of Y. For a higher value of X, you have a higher value of Y. So can I say in first scenario, this is case 1, when X increases, Y also increases? Do you agree with that? You know, this dot shows lower value of X, lower value of Y. Maybe this dot shows higher value of X, higher value of Y. So when X increases, Y also increases, right? And the relationship between X and Y can be represented by a straight line like this. This line can very well represent the relationship between X and Y. Okay, this is called as a linear pattern. So there can be two types of pattern, linear or non-linear. Let's talk about second scenario. Up to this value of X, when X increases, Y also increases, right? So smaller value of X, smaller value of Y, a little larger value of X, larger value of Y. But then after this value of X, when X increases, Y is decreasing, right? So can this line represent the whole relationship between X and Y? The overall relationship between X and Y can be represented by this line or not? Can this line represent the overall relationship between X and Y? No, right? I hope all of you agree. It cannot represent the overall relationship between X and Y. Or can this line represent overall relationship between X and Y? Will this be sufficient to represent overall relationship between X and Y? Not at the moment. You can say this curve can very well represent a relationship between X and Y. I hope all of you agree. Right? This curve can represent very well relationship between X and Y. Right? This particular curve. Right? So you can say that this relationship between X and Y is non-linear. There are always two types of pattern, linear pattern versus non-linear pattern, right? The current neural network can only solve the problem of case 1 and it cannot solve the problem of case 2 because the current neural network is a linear model, right? So linear problems are easy to solve, less complex. Non-linear problems are more complex, are difficult to solve. The current neural network, which is without hidden layer, can only solve case 1 and it cannot solve case 2. Are we good with that logic? Right. So Vijay, I'm going to answer your question in a while. Let me complete this logic. Okay. So the current neural network is a linear model. It can only solve the problem of case 1. It cannot solve the problem of case 2. Now let's talk about a neural network with a hidden layer, right? With a hidden layer. So if we go and let's talk about a neural network with a hidden layer. So we have again 3 input neurons, 1, 2, and 3. And we have 1 output neuron, but at this time, we have a hidden layer as well with 2 neurons. This is L1 layer, L2 layer, and L3 layer. This is input layer, this is hidden layer, and this is output layer. And let's say that all the neurons of layer 1 are connected to all the other neurons of next layer. So we call it fully connected network because all the neurons of first layer are connected to all the other neurons of next layer. This is bias B1, B2, B3. Let's say weight W11, W12, W21, W22, W31, W32, and W41, W51. And let's say that these neurons are N1, N2, N3, N4, N5, and N6. So you can say in total we have 6 neurons in this neural network. In total we have 6 neurons in this neural network, but as input layer neurons are not computational neurons, you can say N1, N2, N3 will not perform any mathematics. Only 3 computational neurons, N3, N4, N5, and N6. So if I look at output at N4 neuron, so can I say N4? Yes, we can select any number of neurons in a hidden layer, Sachi. That's correct. So N4 can be thought of as f of, you can say, let's say that N1 is represented by X1 feature, X2 feature, and X3 feature. So you can think of this as X of W11 plus X2 of W21 plus X3 W31 plus the bias B1. That is the output of N4. N5 can be thought of as f of X1 W12 plus X2 W22 plus X3 W32 plus bias B2. And N6 can be used to represent, you can say that, in N6, the output of N4 and N5 will be input to N6. So N6 will be what? N4 into W41 plus N5 into W51 plus bias B3. Are we good with this part? We call it feed forward process, right? So are we good with weighted sum? So every neuron N4, N5, N6 is doing weighted sum activation function, right? So can we say that this neural network can be represented by these three equations? Do you agree with that, everyone? Right? This neural network can be represented by these three equations, and I hope all of you agree on that point, right? And now you can say that in this case we have three equations, right? We have three equations. Now three equations means three linear models. Now can I say that three linear models when combined together, you can say that let's say first linear model, second linear model, and third linear model can on a whole they can solve a non-linear problem. Three straight lines combined together or three linear models combined together, on a whole it can solve non-linear problem. Do you agree with that? Right? So three linear models or three straight lines combined together can solve a non-linear problem. So you can say now this neural network is capable of solving a non-linear problem, which is the case 2, right? So the moment you have a neural network without hidden layer, it can only solve a linear problem. When you have a neural network with hidden layer, it can solve a non-linear problem as well, right? When you have a neural network without hidden layer, it can only solve a linear problem. When you have a neural network with hidden layer, it can solve a non-linear problem. Now, as many as hidden layer you increase, that many more equations we will have. As many as hidden layers or hidden layer neurons that you increase. So number of hidden layer neurons is developer's choice. It's my choice how many neurons I want to have. There's no rule or mathematics to calculate that, right? And as many as hidden layer neurons that I have, that much more powerful and complex my neural network will become to be able to solve even more complex problem. That means the capability of neural network to be able to solve more complex problem depends on the number of neurons that you have taken in hidden layer neurons, in the hidden layer. If you do not have any hidden layer, it cannot solve non-linear problems. It can only solve linear. If you have hidden layer at the moment, your neural network becomes a non-linear model and it can solve complex problems. And as much as number of hidden layer neurons you have, that much more complex problem can be solved using it. I hope we're good with this part, everyone. Any question you have, let me know, right? So I hope this answers many of your questions about understanding of fundamental understanding of neural networks. And the number of hidden layer neurons in a layer, it depends on us, and layers also depends on us. Why the name hidden layer? Because they don't make, there are layers between input and output. So your data is interacting with input or output. Your data doesn't directly interact with hidden layers, right? So that's the reason we call it hidden layers, as these are the layers between input and output, and your actual data, which could be images and the label, will never interact with the both, you can say, input and output. So it will never interact with hidden layers. It will always interact with input and output. So any base, is there a hidden layer? Mr. Sikhapa, it's like, you don't have formula or mathematics to, we do not have formula or mathematics to calculate it. It's, yes, there's intuition behind how to choose number of hidden layer neurons or hidden layers in general, right? So you can have more layers, 1 layer, 2 layer, 5 layer, 20 layers as well. You can have more neurons in every layer as well. But yes, there is an intuition, or there's a best practice in a way. How do these impact? How if I add more layers, that impacts the performance of a neural network, and how if I add more neurons to the same layer, that impacts the performance of neural network. And we can talk about that, right? We can talk about that the moment itself, right? Give me a moment, I'll explain that. I hope, is that your question about? Your question is that number of hidden layers, or your question is something else? Let me know if I'm correctly understanding your question. So I hope we're good, Abhishek, right? I have answered your question. Why different bias for neurons in the same hidden layer? Yes, in the same hidden layer, because if we use the same bias, all the neurons of the same neuron layer may not learn different patterns, right? So we don't want, all the neurons of the same layer should learn different pattern. We don't want them to learn same pattern. Sorry, we want them to learn different patterns. We do not want all the neurons of one layer to learn same pattern. Otherwise, there's no use of having multiple neurons in the same layer. So each and every neuron will have different values of weights and bias. It's just neurons in one layer will have same activation function, right? Activation function can differ from layer to layer, but cannot differ within the layer. But weights and bias will be separately for each neuron, right? Because we want every neuron to learn different pattern. That's how we can make the neural network solve complex problem. Right. So I hope this gives you a very fundamental understanding about the idea of neural network, everyone, right? Okay, and we are good to move further to look at the idea of convolutional neural network. So after convolutional neural network, Mr. Sekapa, we can talk about the idea of, how does this layers and neurons impact, actually. So here we go, everyone, and we're going to be moving further to the idea of convolutional neural network and looking at that, how does that impacts in general, the understanding of how does that works in general for the image classification task. So what we are interested into convolutional neural network. Convolutional neural networks are part of deep learning algorithms. Deep learning algorithms is a branch of machine learning, which is where we have algorithms which can do automated feature extraction, automated feature selection. If you talk about difference in machine learning versus deep learning, in machine learning problems, we have to do manual feature extraction because we have to manually get the features and feed it to a neural network. It will learn whether the image is car or truck or cycle. Whereas the deep learning algorithm does end-to-end learning, and it does end-to-end mapping of features and identification of features, and it learns from them, right? Generally, machine learning algorithms give you good result with small data sets, but deep learning algorithms require more large data. Machine learning algorithms are quick to train, and deep learning algorithms are more expensive to train, but you can get amazing accuracy and performance from deep learning algorithms compared to that in machine learning. It's limited, right? That's a bit of idea about it, but one of the very fundamental difference in both is machine learning algorithms need manual feature extraction, whereas deep learning algorithms can do that automatically. Every deep learning algorithm is modification to neural network. There are a variety of applications today in deep learning: self-driving cars, ATM rejecting counterfeit notes, smartphone giving instant translation of foreign street sign, or maybe image captioning. You pass an image to the algorithm, it generates this caption as an output, right? So image is input and this caption is an output. Image is input and this caption is an output, right? In some cases, it could be a bit wrong. You can see it says 2 young girls, where this is not a young girl, right? This is a young girl, but this is not a young girl, right? So that's a bit of vague interpretation you can also expect from them. So these are popular applications of deep learning algorithms and used widely in computer vision segment. Deep learning algorithms are very expensive in computational resource when you talk about computational resource part. So today we have the packages which can handle thousands and thousands of images of high resolution with the help of GPU. So GPU based packages are very widely used, and GPU based computation make the process of training the model quite faster. Which earlier if I can recall, in 2010 I was training the model and it was taking around, in 2012 when I was training model, it was taking around 7 to 8 hours to train a single classifier on a good number of images, which got reduced to around 20 to 30 minutes in 2016, and now in 10 to 15 minutes in 2020. Right, so the computational cost has, decreased. The computational capability, or you can say complexity, has decreased quite a lot, and GPU-based infrastructure solutions have made it quite simpler and faster to train the model along with CPU. So to train the model, one of the suitable infrastructure is GPU plus CPU-based infrastructure. You can use Google Colab for the same as well. But to make prediction and to use in production, you not need necessarily GPU-based architecture. Also, today we have a lot of cloud-based infrastructure available from AWS, Microsoft, and from IBM Cloud for training deep neural networks and algorithms quite faster, right? So that also makes it quite easy to train deep learning algorithms. How many data instances can be classified as big? Well, I would say at least 10,000. Yes, Google Colab supports for larger data sets, Nudeep, but you have to load that, mount it from Drive, right? But yeah, you can't process GBs of data in Colab, but at least quite a few GBs of data you can process in Colab. But you will have to mount it through Drive so that your disk space is saved in Colab. Okay, everyone, so here we go now, and how every algorithm in deep learning is modification to fundamental neural network. So you can think of this as a fundamental neural network, a perceptron model. A fundamental neural network with 2 input and 1 output is also called as perceptron model as well. So this can be thought of as single layer perceptron. Then there are a lot of modification to neural network, feed forward neural network, where we have at least 1 hidden layer. We have radial basis neural network, which is a bit of also resembles to supported machines as well, and it uses RBF function as an activation function. We have deep feed forward neural network where we have more than 1 hidden layer, that is 2 or more than 2 hidden layers you have. We have recurrent neural network where the neurons are there, which are recurrent neuron. They take their own output again as input. These are recurrent neuron. A modification to RN is LSTM. LSTMs are very widely used today for developing chatbot application, language translation, time series forecasting, stock forecasting. Many of these very popular applications are solved using LSTM. We have modification to LSTM called GRU, very widely used for text summarization and text generation as well. Autoencoders, very widely used for dimensional reduction, denoising images, removing noise from images, very widely used for fake image generation, and the other applications include image generation and anomaly detection, fraud detection. Variational autoencoders are very popular for fake image generation, right? Denoising for removing noise of images, right? So if I have to remove noise from images, I can use this particular version of autoencoder, right? And this could be something used for sparse autoencoders for recommendation engines. So autoencoders are part of unsupervised machine learning algorithms from neural networks. So autoencoders are a way of using neural networks with the help of unsupervised machine learning, right? Whereas these all are part of supervised, you can say these all are part of supervised machine learning, right? Then there are a lot of other modification to neural networks, which could be Markov chain models, Hopfield network. These are not very widely application oriented fields. Markov chain models could be used for model optimization or system optimization, system identification. Hopfield network. Boltzmann machines are also used for system identification. RBM, a modification to Boltzmann machines, are very widely used for recommendation engines. So even Netflix recommendation uses a quite similar model, a neural network for recommendation engine up to RBM. We have convolutional neural networks very widely used for image classification kind of task, right? So matrix manipulation or matrix processing, if you have to do, which is like image processing, a lot of cases, and image classification for this different variants of, or image classification and object detection. Many of these tasks, different variants of convolution and deconvolution networks are very widely used. We have generative adversarial networks today, very popular research happening up in GAN, very widely used for deep fake, I would say, fake image generation, fake audio video generation. They are generators. Most of the neural networks and algorithms are discriminators, where these are generators. Others include liquid state machines, ELM models, eco-state machines. Networks are other networks widely used for pattern identification, system modeling. These are few applications of this, right? So, but not very very popular, I would say, in terms of commercial application development, right? So yeah, that's the idea so far. I hope you're good. Okay. And supported machine widely used for image classification as well. So SVM widely used for image classification. They were mostly developed back in 1992 by Wapnick for the task of handwritten text classification. But from there, they are very popular so far for their performance on image classification tasks. Right. So that's an idea about it, everyone. But the most popular neural networks that we use today in a lot of commercial applications, I would say, are deep neural networks, convolutional neural networks, and recurrent neural networks, and a modification to RNN, which is LSTM. But what we are interested into is convolutional neural network, and we are interested in understanding what is CNN and how does that works out. Here we go with that. So convolutional neural networks are widely used for tasks of image classification, image object detection, localization, and segmentation. One of the example could be, let's say, face recognition. Convolutional neural networks can be used for. Let's understand how does it works and what kind of problem can we solve using this. Here we go. A convolutional neural network can be thought of, or you can say you can split that into two segments. You can split a CNN into two segments, and the first segment could be, you don't have the annotation option here. Okay, the first segment could be, you can split a CNN or a convolutional neural network into two segments. The first segment is feature detection segment, and the second segment is classification segment. The first segment is consisting of a feature detection unit, and one feature detection unit is consisting of three important steps. The first step is convolution, ReLU, and pooling. Right, these are three important steps of feature detection unit. And the second segment consisting of classification segment, where we have we have layers, right? Layers of neurons, and these neurons do simply weighted sum activation function. We have just seen now, that's what this classification segment does. They simply do weighted sum activation function. So each box is representing one neuron, and each neuron does weighted sum activation function, and that's how they do classification at the end of the day, right? So I hope we're good with this part, everyone, right? So two segment, feature detection segment and classification, right? I'll repeat again, feature detection segment and the classification segment. And in feature detection segment, we have one unit of feature detection consisting of three steps, convolution, ReLU, pooling, another unit consisting of other steps, convolution, ReLU, pooling. So, these are the three important steps that are important to understand. And then we have classification, and what they do is they do simply weighted sum plus activation function, right? So they do weighted sum and activation function, whereas this do what? Convolution, ReLU, pooling, right? So you can split CNN into two segments, as you already learned the part of classification, right? So what happens in classification? Every neuron does weighted sum activation function, What we need to learn is that how a CNN is going to be able to identify automated features, right? And how convolution, ReLU, and pooling actually works in general, and what's the logic behind that, high level logic we're going to be understanding about it, and understanding that how is this can be used to help the neural network detect good features, which can then be consumed by classification segment to do the job of classification. So are we good to check out this part, everyone? Good to go ahead. Right, I hope we're good to go ahead to check out this part. Here we go. So what is exactly feature detection and classification? If you're not able to make sense out of that, let's take an example to understand that here, right? So let's say that there is a kid, and to a kid, what we do is we pass, so there's a kid, and to the kid we pass, let's say, we give the kid 100 pictures of cars and 100 pictures of truck, and the kid has not seen any vehicle in his or her life. We give a task to the kid, 100 pictures of cars and 100 pictures of trucks, and ask the kid that you have to learn from these 100 pictures of cars and 100 pictures of trucks how to identify a car and how to identify a truck. But the kid has not seen any vehicle in his or her life. Now the first thing the kid is going to do in this case is kid is going to learn how to identify a vehicle. The first step is going to be the kid is going to learn how to identify a vehicle. This is the process of, we call it feature detection. So kid is going to identify, by scrolling multiple pictures of vehicles, kid is going to identify that a vehicle has something called a wheel, which is round in shape. A vehicle has an object which is, you can say, somewhat like this, slant in shape, like the top of the car. A kid has a rectangular object as well in the car. These are the different features the kid is going to learn how to identify a car or a truck or a generic vehicle. This is called as feature detection, right? This is going to help the kid to understand what in this picture, what is background and what is car. Where is the car? Where is the background? Where is the car? Where is the road? Where is the car? Where is the building? Or a truck or a road or a truck or a building. This is the process of feature detection. When the kid has not seen any vehicle in his or her life, the kid is going to learn how to identify a vehicle. That's the first step. Once a kid is going to be able to identify a vehicle, then kid is going to learn that, well, whenever it comes to wheels, right, whenever it comes to wheels, if the wheels are 4, it's usually a car. If wheels are more than 4, it's usually a truck. Kid is going to learn whenever there's a slant object like this present, right? So this is present, or you can say this is true, it is car. When this is false, means it is not present, it is truck. Kid is going to learn whenever there is a rectangular object and height and width are higher, it is truck, and height and width are lower, it is car. Right? So the second step is what we call classification segment. This is what we call as classification segment. This is how a kid's or a human brain actually functions. A human brain actually works, right? A human brain actually first step does is feature detection, which is unsupervised learning. Nobody tells us how to identify vehicle. We on our own learn how to identify vehicle, right? Nobody tells us how to identify human versus animal. Nobody tells us how to identify a car versus, a table versus you can say the floor, right? We on learn that, which is unsupervised learning. So feature detection is always unsupervised, whereas classification is supervised, because somebody has to tell that this is car, the name of this vehicle is car, and the name of this vehicle is truck, right? So somebody has to tell us that. Okay, so in general, with machine learning algorithms can only do classification. They cannot do feature detection. You have to manually do feature detection and feed features to them. Whereas deep learning algorithms like convolutional neural network is going to be able to do both the jobs. So you can say convolutional neural network works almost as good as the way a human brain works and does the job of different object detection and classification. Right. So first step of the first step of this neural network, which is, you can see that the convolution, ReLU, and pooling, these steps are going to help in doing feature detection. The next step, classification, weighted sum activation function, those kind of neurons are going to be doing up the job of classification. I hope you're good with that part. Right. So now we need to understand what is convolution, what is ReLU, and what is pooling, and how these 3 steps help in extracting right features, which then a neural network can learn. Are we good with that? Everyone good to go ahead, check out that. So here we go. And we're going to be understanding first the idea of what is convolution, what is ReLU, and what is pooling. So ReLU is simple activation function, and pooling is a very simple approach of downsampling, right? So let's go ahead with them one by one. The very first step that we're going to be looking at is the idea of convolution. Understanding the process of convolution, how does that works, and what do you do as part of that. Let's say that we have a picture like this, right? So we have a picture here, and we also have a pixel representation of that picture. And so first, let's say that the picture is actually more of a, we have a picture of an X, right? So let's say we have a picture of a digit called a cross, right? Or X, like A, B, C, D, X, Y, Z. Okay, so we have a picture of an X over here. This is a picture. And let's say that we can talk about more of a pixel representation of this, right? So we have pixel representation of this. Yeah, let's say that this is it. I wanted to actually go for one more level. Let me also decrease this a bit. Okay, so we have a pixel representation of this, which is, let's say, Wherever there is white color, we'll say it is 1. So for every white color box, we'll say it is 1, 1, 1, 1, 1, 1, 1, 1. And wherever there is a black color, we'll say it is more of 0, 0, 0, 0, 0, 0, 0, 0, 0. So black color we are saying just for simple understanding so that we can make sense out of this, but generally as you know that the values of pixels are going to range between 0 to 255 for grayscale, and for color again it's going to have 3 values, right? So wherever there is a you can say white color pixel, we can say it's 1, 1, 1, 1, 1, and 1. So wherever there is a white color pixel, it's 1, and corresponding to black we have 0. So this is the left hand side we have image, and the right hand side we have a pixel representation of the same image, right? So we can say that this is an image, right? Or this is an image, and this is pixel representation of image. Okay. Now this is an image. What we do as a part of convolution is, as a part of convolution process, we take a filter, right? So we're going to take a filter, let's say, which is going to be of size 3 by 3. And this filter is going to help us generate a feature map. And let's say that looks like this a bit. Okay, so we're going to have something called a filter here, and we're going to be understanding that how the process of convolution actually works with the help of filter and a feature map. Here we go. Let's say that the values of filter are 1, 0, 0, right? Like this, more of let's say 1, 0, 0, 0, 1, 0. We have taken it randomly. We don't have to decide the values of filter in programming approach. So what actually is the process of convolution? In the process of convolution, we map every filter, and scroll it on the whole image, right? So we do like this. Let's say that first we're going to map this filter on this part of the image. On this part of the image, we're going to map the filter, right? So if we try to map the filter here, can we say that first value is matching with the first value filter, second value is also matching, third value is also matching. So wherever there is a match, we'll say +1, +1, +1. Second row, 0, 1, 0, matching with 0, 1, 0. Again, we'll say for every match, +1, +1, +1. Third row, 0, 0, 1, matching with 0, 0, 1. We'll say +1, +1, +1. Divided by the total number of values, we can say that the total number of values are 9. So divided by 9, it's going to be 1. That means the map of this filter on the top left corner of the image is 1. So we'll say here it is 1. The outcome is 1. That means the feature map says that this filter is having map of 1 on the top left corner of the image. Now once we have mapped this, then we'll go for one step next, and we'll scroll to the left and now do the mapping here. Now when we do the mapping here, again we're going to cross check it, right? So this 0 is not matching with this 1. So we'll say wherever there's a mismatch, -1. 0, 0 is matching with 0, 0. So we'll say +1, +1. Second row, 1, 0, 0. And here we have 0, 1, 0. So first value not matching, second value not matching, third is matching, right? So we'll say -1, -1, +1. Third row, 0, 1, 1. It is 0, 0, 1, right? So we'll say +1, -1, +1. Divide by 9. So we have total 4 minuses. We'll say 1 by 9, which is 0.1. That means the match of, or the map of this particular filter on that part of the image is 0.1. Right? Like this, we next go ahead to the next step where we scroll one step further to the left and now do the mapping here. Like this, we'll keep on scrolling through the whole image, right? So 0, 0, 0, you can say -1, +1, +1 for first row. Second row, +1, -1, -1. Third row, -1, -1, -1. There are 3 pluses. You can say it is -1 by 3, which is -0.33, a negative value, right? Similarly, we keep on scrolling down, left and left, again, we'll map it here and we'll get certain value, right? And then we'll map it here, again, after that, we'll map it here and get certain value. So you can see if I map it here, the certain value could be 0, 1, 0, which is like -1, -1, +1, 0, 0, 1, +1, -1, -1, 0, 0, 1, +1, +1, +1. So we have 1, 2, 3, 4 minuses, which is 1 by 9, and you can say that 0.1. So can we say that wherever there is a very good map, we will have highly positive value, maybe like 0.8 or maybe 0.7. Wherever there is a mismatch or slight positive match, we will say slightly positive value could be 0.2 or 0.3. Where there is a higher mismatch, we may have negative values -0.4, -0.6, -0.3, -0.8, right? Slight match 0.3, 0.4, 0.3, -0.9, very highly mismatch, very good match 0.9. Like, so we may have, or maybe this would be +1 as well, right? So we make it certain values in the feature map. Wherever the filter is matching very heavily, we'll have a higher positive value. Wherever it is slightly matching, slightly positive value. Wherever it is mismatching, negative value. Wherever there is a higher mismatch, higher negative value. Right. So that's how we get, that's how we get the feature map generated. So Justin, is that the question about the convolution process, the feature map calculation? Is it? Okay. Right. So here we go. Let's talk about that. Yeah, Amani, that's correct. It's technically it is actually a weighted sum, where filters are the weights. So technically, when you look at the filters, they are actually the weights of the neural network, right? And weighted sum between the portion of image and the filter. The filter itself is the weight. And so whenever it comes to a convolution neural network, we don't decide the values of filter. We just initialize filters with the random values. And in the process of convolution, the filters values get convolute with the images, which is not exactly as weighted sum, right? The way we do in standard weighted sum, x1 w1, x2 w2, not exactly that weighted sum. It's more of convolution of that, which is multiplication plus averaging done both at the same time. And you can say it is also averaging done at the multiple channels, as the filter may be of multiple channel size as well. Right, so we call that process as the mathematics as convolution mathematics, right? And definitely it is when I say the values outcome will be representing the same thing as match. So mathematically it is the mathematical convolution of filter, which is the weight with the image, right? So Juhi, you will get answer to that question in a while. And okay. So here we go. Let me just repeat this part in a quick go, right? The idea of this calculation, the idea of calculation of the feature map, right? And so here we go. You can see that here, everyone. What we do is we try to map, right? So we try to map a portion of, you can say that first I may want to map this portion, and second I may want to map this portion. So what we do is the filter maps, scrolls on the whole image and maps the portion of image, right? So maps this portion, this portion, this portion, and this portion, and then comes down this portion, this portion, this portion, like that. It is simply going to calculate, map out on the whole image on how much image is actually similar, to the whole, to the feature. And it's going to calculate like this, right? Like this, it's simply a filter rotates on the whole image step by step, step by step, step by step, one by one. And how much is size that you want to rotate, it also depends on us, right? So we call it strides. So we can make it jump 2 by 2 as well. We can make it jump 1 by 1. Now let's say that if we talk about this particular calculation, so this particular calculation is going to happen in what way? So just let's look at here. What we do is we simply map the value. So you can say that this 0, right? This 0, we match it with this 1, right? So it is mismatching, so we'll say -1. This 1 is mismatching, we'll say -1. Abhishek will talk about that downsampling. That comes as part of max pooling, right? And then we have this 0 is matching with this 0, so +1. Wherever there is a match, you can say +1. Where there is mismatch, -1. 0 to 0 match plus 1, 0 to 1 minus 1, 1 to 0 minus 1, right? Third row, 0 0 1, 0 0 1, complete match, plus 1 plus 1 plus 1. So we have 1 2 3 4 minuses and 5 pluses. So it is, you can say that it's going to be 1 by 9, which is going to be 0.1. Are we good with that, Justin? How is it calculated? Right. So like that, you see, wherever the filter is very good having match. For example, in the very first case, it was having very good match. So wherever there's a very good match, we may get higher value like 0.8, 0.7, or 1 as well. Wherever there is a higher mismatch, right, we may get negative value, minus 0.6, minus 0.3. Wherever there is a slight match, we may get value like 0.3, 0.4, 0.6, or 0.8, or 0.3, 0.2, 0.1, or 0.2, right? Like that, we may get a feature map. So are we good with the idea of calculation of feature map, everyone? Right. Now, in the process of convolution, every filter is actually thought of as a weight. And as a part of development, your job is not to decide the values of the filter. So you don't decide that. The values of the filters are randomly initialized. When you train the neural network, the filters update and they learn the features, they attain the pattern of the features, right? So you can say one filter may, if I'm doing face recognition, one filter may learn how to the shape of eye, another filter may learn the shape of lips, another filter may learn the shape of nose, the shape of ears, and the shape of maybe chin, and something else, the shape of eyebrows, like that, right? So initially, when you train the neural network, you initialize filter values of the filter randomly. While training, these filters will learn and adapt those patterns, those features. As a programmer, you need to decide the number of filters and the size of filters. The two hyperparameters which are very important over here, number of filters and the size of filters. There are other hyperparameters as a part of strides and padding as well, but these are the two important hyperparameters. And this is the output of filter map. The feature map is the output of you can say the convolution. So you can say that the image is actually convolution of the filter and the feature map. The image is actually convolution of the filter and the feature map. So yeah, that's an idea about it, everyone. I hope we're good with the understanding, fundamental understanding of convolution process, right? So why it is needed and how does it help? You will get a very clarity coming further. So there's a question, how to choose filter size? Well, that's a good question, Fatma. So the idea of filter size is, filter size actually represents the size of feature which is going to be extracted, right? Now, if you take a larger size of filter, the process of convolution may skip fine-tune or complex features, right? Now, let's say that if I have two jobs. First is I need to recognize traffic signs. Traffic signs are a horizontal line, a vertical line, across. The other is face recognition. So out of traffic sign versus face recognition, which may have complexity of features, which may have higher complexity of features? In which case, more complex features are there? Is it in traffic signs or is it in face? Right? So if I show you traffic signs, let's say look like this. Right? So traffic signs looks like this. So is it traffic signs are going to have more complex features, or is it a face is going to have more complex features? Yeah, same thing for color images as well, Justin, right? So you might say that traffic sign will be easy because they are simple triangle, a horizontal line, or a vertical line, right? They're simple, easy to interpret. Face will have more complex features. So if I have to identify more complex features, I can take a filter size a little larger for traffic sign, because the larger filter size that you take, the faster will be the process, and the smaller filter size that you take, the slower will be the process. At the same time, the smaller filter size that you take, more complex and minute features will be identified. The larger the filter size you take, that much small features or complex features will be skipped. So for traffic sign, I can take, let's say, 10 by 10 filter, or 5 by 5 filter, or 7 by 7 filter. Whereas for face recognition, I may want to go for necessarily 3 by 3 filter, like that. So I hope that gives you an idea about the filter size, right? Okay. So it mostly depends. It's a hyperparameter one way, and it depends on what complexity or what level of complexity of features you want to identify. Right. So let's go ahead further and get into this part and understand the idea of convolution a bit more, in an easier way. Here we go. Right. So this is the process of convolution. Here we go. So you can see here that we have an image, right? So we have an image here, and this is an image. And as we know that a color image will have 3 values, red, green, blue. So you can say all the rows, all the columns, and 0. So this represents the red part of image, this represents the green part of the image, and this represents blue part of the image, RGB, like that. This is our filter F1, this is our filter F2. This is the red part of the filter, green part of the filter, blue part of the filter. The example that we have seen, which was on grayscale, this is an example of color. This is a red part of filter, green part of filter, blue part of filter. And this is the feature map 1 for F1 filter. This is the feature map 2 for F2 filter. Right. So filters simply scroll through the whole image and try to simply calculate feature map, which shows the mapping of the filter on that particular image. So this is the process of convolution. Are we good with the process of convolution, everyone? And in this case, you can see that the filter is skipping 2 rows and 2 columns, right? So this skipping of 2 rows and 2 columns is what we call strides. So we can also control stride, as in stride we want 2, or we want 1 of stride equals to 1 or stride equals to 2, like that. That can also be controlled. And there's an extra, there's an extra column of 0, an extra row of 0 added, which we call as padding. Because if you take the convolution process, it may happen that the process of convolution may skip, or may scroll on the corner part of pixel very less, whereas very much on the central part of it. So we add padding as well, right? So this is called as padding. And stride is like the number of rows and columns it skips, right? So these are different hyperparameters in convolution process. So filter size, number of filters, the stride value, padding are the 4 important and popular hyperparameters in the value of convolution process. In the form, in the convolution process. The value of filter, Tushar, when we train the neural network, we don't decide it, we randomly initialize it. When the neural network learns from thousands and thousands of images, it learns and what features are important, and those features are learned and showed in the form of filters, right? So you can say that when you train the neural network with the pictures of trucks and cars, the filters initially will be random values, but at the end of training process, one filter may recognize wheel, another filter may remember the pattern of this slant architecture, another filter may remember the pattern like this, right? So different filters will learn different features. Initially, when you train the neural network, you have to initialize the values of filter randomly, because you don't know that those features. That's an idea. I hope that answers your question, Tushar. Right? Filter value fixer. No, filter values will keep, you see, filters are nothing but weights of the neural network, Balakrishna, right? So when you train the neural network with the process of gradient descent, the errors tries to reduce and the filters values keeps on updating. So initially when you train it, the values of filters will be random. In every iteration of training process, the values of filters will keep updating, and at the end of the day, you will have the filters with the best values, right? So at the initial level, when you train the neural network doesn't know that how a wheel looks like how wheel of a car looks like, how bonnet of car looks like, how other part of the car looks like. Every filter will have just some random values. At the end of the training process, the filter will have best values, or you can say the filter will have will learn the features to identify the wheel and the bonnet and different other part of the car. If that answers the question. There's a question, what is the operation performed between the image and the filter? Do we have any averaging? Yeah, definitely there is an averaging. If you have multiple channels, there is an averaging. There is an averaging between multiple channels of RGB. So you can see that in image also we have RGB, and in filter also we have RGB, but in map we don't have RGB, right? So the size of map, that means the number of maps will be equal to number of features, right? So there is an averaging among multiple channels of RGB. Right. Can padding be only done by repeating the boundary values? No, they are not done by repeating, just by resetting the bounding values to 0. So we just, we don't repeat it, otherwise the pattern will change. We make the bounding values as 0. That means a black color border that you add. So as a part of padding, Juhi, what we do is, we are ultimately adding a black color border. Right. So output volume, just in output volume is the same process that we have learned. It's a bit of multiplication plus averaging here. Right, so multiplication plus averaging here, and multiplication plus bias and averaging across 3 channels. So it's almost the same process: multiplication plus addition of bias and averaging across 3 channels. That's how the output volume or the feature map is being calculated. How should we make image to graph scale for better? So Abhishek, in a lot of cases, you don't want to manually manipulate images, right? So you don't want to do a lot of pre-processing in order to identify better features. It just, you need to make sure that images have effective visual. For example, the images should not be completely dark or completely black or completely white, right? So you need to manage the bit of transparent, you can say, brightness in the image. You need to manage a bit of visibility of features in the image as well, noise in the image. These can help the neural network to do better feature extraction. Okay, so this was the idea of convolution process, everyone. I hope we're good so far, right? B0, B1 values, no, they are also weights. So B0, B1 are bias here, we say, and they also keep on changing. No, here we don't talk about mean, median, mode filter, right? So these are, when we say filters, these are more of neural network based filters, right? So they are not, they are not using a specific fixed statistical technique, right? The values of filters keep on updating. They are not fixed on a specific method, right? So when you train the neural network, the values of filters change, and at the end we get the best values. Yes, it is that in across multiple channels we can apply mean, median, mode. We generally go for mean because initialization of filters is normal distribution of values of filters. So we always go for mean for normal distribution. Next step is ReLU as a part of feature detection. So let's understand this. ReLU is a function which is fx equals x if x is greater than 0, 0 if x is less than or equal to 0. This is the simple formula for ReLU. All right. Fx is x if x is greater than 0, or 0 for x less than 0. Or you can also call it, it will do max of x and 0. That's what ReLU formula is. Both are same thing, right? So what ReLU will do is on the top of feature map. So ReLU is applied on the top of feature map. So on the top of feature map, what it will do is wherever there is a positive value, it will keep it as it is, as you can see. But wherever there is a negative value, ReLU will truncate it to 0. Right? Wherever there is a negative value, ReLU will truncate it to 0. Are we good with the idea of what ReLU is doing? We'll link it to logic as well. ReLU stands for rectified linear units, and it's a simple activation function, fx equals x for x greater than 0 and 0 for x less than 0. Are we good with the idea, everyone, what ReLU is doing here over here? Right, I hope we're good so far with the idea of what ReLU is doing. Right, now imagine a situation in which you have image of a human face, right? So imagine a situation where you have an image of a human face, which could be, let's say, which could be, we're gonna be, reaching to time, I believe, but yeah, let's say that this is the picture that we have, which is a picture of a human face, and if we apply the process of convolution and ReLU on this, right? So when you apply process of convolution, let's say that you're applying a filter which is having I, right? So you're applying a filter which is having I, right? So the filter is having the portion of, you can say I. The filter has a pattern of I, right? Now when you rotate this filter, what will happen is on the background, can I say on the background here we'll get a negative value, right? So if my filter contains I, if I scroll my filters on the top left from here, we'll have negative values here, everyone. Can I say like that? We'll have negative values all over here. Do you agree with that? If we do convolution process, during the convolution process, if we take a filter of I and rotate through the whole picture, we'll have negative values here, and we will have very positive value on this portion. On this portion, we'll have positive value. On this portion, we'll have positive value. Maybe the lips, the shape of lips also look much more like I, so we may have positive value here as well, right? And if I scroll down, we may have slight positive value here as well, because this also looks a bit like small I. We may have slight positive value here as well, slight positive value, right? We may have very positive value for actual I. We may have very positive value for actual I, slight positive value for lips, because that also shape looks like I, right? And rest of the part, we may have negative values, negative values, negative values, right? Now what happens when you apply, this is the process of convolution, the output of convolution process. Are we good with this part? Right? So on the backgrounds, we will have negative values. On actual I, we will have very positive value. On the lips, we may have slight positive value. On the shirt buttonhole, we may have slight positive value. Here may have slight positive values as well. Right? Now, this is the outcome of convolution. When you apply ReLU, what will happen? wherever there was negative value, the negative values will become what? Relay will make, relay will, what changes relay will make? So relay will make all the negative values to 0, right? That means if you look at color perspective, wherever there was a mismatch, all of the values will become 0. That means it will become black color. 0 means black color. That means wherever there was no eye, that will completely become black. Wherever there was eye, that will remain as it is, almost as it is, right? So rest of the process other than eye, the whole mouth, background, hairs, ears, nose, black. The actual eye, lips, and this portion, which are possibly eye, will become remain as it is, right? Are we good with the logic here? The actual eye, lips, and this portion, which are possibly eye, remain as it is, and the rest of the whole part will become black in color, or you can say 0, right? This was the output of ReLU. This is what ReLU does at the moment. The next step, which is the third step of max pooling, right? Max pooling is also, Abhishek, we call it down sampling. You had a question regarding this. So max pooling, or we call it down sampling. This reduces the size of image. So what we do in max pooling or down sampling is, if I have an image of shape 4x4, we have an image of shape 4x4, let's say, we take a pool window. So let's say my pool size is 2x2. I take a pool window of 2x2, and from this 2x2, which is the maximum value, so from this 2x2 we have maximum value is 6. So we will represent now this 2x2 window by only single value 6. We pull the maximum value from this. Similarly, this 2x2 window, what is the maximum value? The maximum value of this 2x2 window is 8. So we will represent this whole 2x2 window by only one value, which is 8. Similarly, this 2x2 window, the maximum value is 3. So we will represent this whole 2x2 window by single value 3. This 2x2 window, the maximum value is 4. So we'll represent this 2x2 window with a single value is 4. This is what we call max pooling. So you can say why we call it down sampling. As you can see, the shape of image from 4x4 has got reduced to 2x2. We call it down sampling. So are we good with the idea of max pooling, everyone? Are we good with what max pooling is? What is the mathematics behind max pooling? So it simply pools the maximum value in a specific pool window or pool size. 2x2 pulling the maximum value. 2x2 pulling the maximum value. Right, now coming back to the same, again the same thing here, right? Coming back to this. So what will happen when you apply ReLU? Everything will become black, and the real eye, lips, and all of these will remain as it is. Now when you do max pooling, what will happen is the maximum value will be what? The one which are corresponding to the real eye are going to be the maximum value, and these values will pulled out, and the values like lips and all others will be left. Right? So the real eyes will be pulled out, and all the slightly positive values will be left. So at the end of max pooling, you will have eye extracted from the image. And this way, wherever is the human face, for example, the human face is on this part of the image, or on this part of the image, or on the corner, this process will be able to identify where is the eye. Right? So you need not to tell in the image where is background, where is eye, where is not eye, where is eye. You need not to do the feature extraction. The algorithm at the end of the day of convolution, ReLU, and pooling, 3 steps combined together, it will be able to do effective feature extraction. Are we good with the idea, everyone, how feature extraction is happening with the help of convolution, ReLU, and pooling? How the feature extraction is happening with the help of convolution, ReLU, and pooling, right? So these 3 steps at the end of the day will be able to extract good features, right? And that's how the feature extraction works out, right? And so yeah, if you apply that on the pixels, you can say that, if you apply that on digits, initial levels of convolution, ReLU, pooling are going to learn low level features like boundaries or edges. Next level of convolution, ReLU, and pooling are going to learn high level features like maybe circles and layers. So one convolution, ReLU, and pooling constitute one unit of feature detection. You can use such multiple units of feature detection and make the neural network learn multiple different levels of features, right? That's how it works, right? So you will have Sriram, one filter applied, one time, and they can be multiple filters. If there are multiple eyes present, you can say 2 filters will occupy or maybe carry that out. Even one filter may give you both the values, because in downsampling, you don't get only one output, you get 2 outputs as well. All right, so that's an idea about it, everyone. And Similarly, if you talk about face recognition system, if you pass the images of faces, the first layer of convolutional pooling may help identify the boundaries or edges. The second layer of again convolutional pooling may help identify the features like eyes and the features like nose and the features like a bit of ears, nose, eyes, right? And one of the layer of convolutional pooling may help identify the exact face from the whole image frame, right? That's how the idea of convolutional Lillian pooling help in identifying the features, extracting the features, which can then be fed to the classification unit for doing classification, and it can do the image classification in general. Right, Jovi, we generally use same window size, which is 2 by 2. We do not go for higher or lower than that, because lower than that is not possible. Higher than that is will help you, will lead you to lose a lot of information, because when you take 2 by 2, the image size is halved from 4 by 4. It is becoming 2 by 2. If I take 3 by 3 window from let's say 18 by 18 image, I may have a 2 by 2 outcome, which is like very much loss of information I may have. So in 95% of the cases, you will go for always 2 by 2, not even less than that, not even higher than that for max pooling, right? So yeah, that's an idea. Just if it is about read about a bit of output volume, or a bit of read about the convolution part, how is that calculated? I would strongly encourage you all to read a research paper, which was the very first paper published by Jan LeCun. So the guy who developed this is Jan LeCun, and he published very first paper on convolutional neural network back in 1998. So if I search for the paper, Jan LeCun paper on CNN, I guess this is it. This was the very first paper published on, yeah, this is it. A very detailed paper. And Jan LeCun currently heads, as a research director, he heads Facebook as a research director of AI. And he's the guy who developed this algorithm back in 1998, along with Yeshua Benigo. Benigo is also a pioneer behind LSTMs as well. Right, so this is a very good paper. I can pass on link to this paper in the chat box, and if you have time, I would encourage you to read this paper. It will give you very fundamental understanding about the process of convolution, how output volume is calculated. And this is based on the LeCun's hypothesis, which was the very first hypothesis. But then after that, there has been a lot of improvements in the calculation of, on this particular, yeah, both are Turing Award winner, Sriram, that's correct. So there has been a lot of improvement on this, on this approach of convolution process. But yeah, this was the very first, you can see the neural network of CNN developed by Jan LeCun. So convolution, max pooling, and dense, like that for weighted sum activation function. So I would encourage you to try to read this paper once, and this will help you a lot with the understanding of convolutional neural network. And he developed this application for image classification for digits of shape 32 by 32. And it's a bit lengthy, but very much useful and useful paper, I would say. For recording of this session, definitely, I think I'm not sure about that. I think, yeah, it's happening. The recording is happening. So I believe we should be able to share you at the end of the webinar. So today's part of the webinar was more on theoretical understanding of CNN, everyone, and understanding of how convolution process works out. In tomorrow's session, we're going to be practically working with this. In tomorrow's session, we're going to be practically programming convolutional neural networks on a particular use case of image classification, understanding how does it works. And we're going to be exploring the concept of transfer learning going further. What is transfer learning, and how does that works out, and how can we use and employ transfer learning for building applications in general, and what is the use of transfer learning, where the word is coined from, and how do we program transfer learning in general as well. We'll be looking at that, which is going to be very, very interesting topic, I would say, for tomorrow's session. All right, so that's an idea, everyone. I hope we're good so far. With that part, we'll be ending up here. Regarding PPT, yes, Tushar, we will be helping out with that. We'll be sharing an email at the end of the webinar tomorrow. So tomorrow also we have the second part of this webinar, everyone. Please make sure that you all join by 8 in the morning, and we have the second part of this webinar starting up tomorrow, which is going to be a hands-on session on convolutional networks, and also going to be talking about transfer learning as well. Right. So yeah. So we are done with today's part. We'll meet back tomorrow. Thank you for joining the session today. See you all tomorrow. Okay. Thank you all for your feedback, and see you all tomorrow. How to write activation probability from visible to hidden layer. Uh, I didn't get you actually your point, Sachi, right? So in terms of probability, we mostly define the mathematical working of multiple layers. So we write a framework in which we the data is going to send from one layer to another layer, and in between, generally, when it comes to hidden layer, we mostly do not nowadays do not use a lot of probabilistic activation functions. Rather, we use activation functions like ReLU, which does the switching of neurons, and that's that's how it works. If you can a bit more elaborate your question, maybe I should be able to answer. Okay, everyone. So thank you for joining, and with that part, we'll be sort of ending up here. So the link to the paper. The link to paper I have shared in the chat box. Those who have missed it. Will check out with that, Balkrishna, where I need to connect to the point of contact who would have shared you the details about the webinar. We'll need to check with them.